everybody from the palatial Keeler Estate in Northern Virginia. We're not all there. That would be awkward. But I'm here. I'm back in the sunroom. It is spring in the Washington, D.C. area, and that means no more indoors for me. My name is Brad Keeler. I'm the director of the Geo-Institute, and we are so excited to have you back with us this afternoon for episode 2 of 3 in the Maccaferri Live series. If you have stumbled upon us and you don't know anything about the Geo-Institute, we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and we are part of the American Society of Civil Engineers. And if you like what you see today, and I think you will, you came to the right place. This is where we give you the good content, people. Click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. Here to moderate / host / answer your questions, well, help answer your questions / do other things this afternoon is Geo-Institute Technical Manager Christina Scott in her first moderating role. So don't put too much pressure on her, everybody, but she's going to do a great job. She's got her green on, St. Patrick's Week. She's going to introduce our speaker today, a little bit about the topic. Christina, take it away.
Thank you, Brad. Thank you for that introduction. I'm very happy to be here today and moderate this session. So I'm very excited. Everybody, welcome to the second episode of the Maccaferri Live series. For today, the topic is flexible facing system for painted, drapery, and saw nailing applications. The systems provide control and prevent rolling of failing of rocks on slopes. And the presenter is Mike Koutsaouris. Mike is the Geohazard Mitigation Business Unit Manager of North America for Maccaferri. Mike has a bachelor's degree in civil engineering from North Carolina State University and a master's degree in civil engineering from the Georgia Institute of Technology. Mike is a geotechnical engineer with over 34 years of experience and has authored and present several technical papers at various industry conferences through his career. So good job. For the past 6 years, Mike has been an officer for the Association of Geohazard Professionals and chairman of the ASTM Subcommittee for Geohazard Nettings. On today's live series, he's going to be talking about the Maccaferri services and products. And if you want more information about Maccaferri, visit maccaferri.com. Other than that, Mike, thanks for being here. Oh, one more thing is, if you want to know more about the first episode, check it out in our YouTube channel. The first one was simple drapery system for rockfall mitigation. Very cool images on that presentation. So no further ado, Mike, the floor is yours.
All right. Thank you, Christina. Let me go ahead and share. Okay, hopefully we're all seeing this now.
Yes.
Good afternoon. My name is Mike Koutsaouris. I'm the Geohazard Mitigations Business Unit Manager of North America for Maccaferri. For those of you not familiar with Maccaferri, Maccaferri was established 144 years ago and has been manufacturing and supplying geohazard mitigation systems throughout the world for over 60 years. We're recognized as a leading innovator and manufacturer of geohazard mitigation systems, and we currently have over 3,000 employees and we service over 130 countries worldwide. I'd like to welcome you all to our second geohazard mitigation live stream webinar this afternoon on flexible facing systems for pin, drapery, and soil nailing applications. We do offer a 1-hour PDH certificate if you're interested. I failed to mention that at the last webinar, but if you did view the last webinar, we'll be glad to provide you with a PDH certificate for that one as well. Feel free to email me. I'll It's m.kutsarias@maccaferri.com, or you could find my email on our website at maccaferri.com. As mentioned, this live stream webinar is the second of 3 geohazard mitigation webinars in which we'll discuss how steel wire mesh is used as a flexible facing for pin drapery and soil nailing systems. Webinar 3 will be held next month on April 23rd, where we'll discuss Rockfall Barriers and Attenuators. To give you a glimpse of what a geohazard is and what it can do, this is a large landslide that occurred in February of 2010 in southern Italy. The landslide was triggered by cumulative precipitation over the preceding 20 days, which exceeded the 100-year rain event, and which followed 4 to 5 months of heavy rainfall, totaling about 150% of the average rainfall for the period. This picture is from a helicopter showing the devastating effect of that landslide. The landslide caused nearly 2,300 inhabitants to be evacuated with high economic losses, and all communication was cut off for several weeks. We generally describe a geohazard as a geological condition involving short-term and long-term geological processes from small to very large scale that may lead to widespread damage or risk. We classify geohazards based on whether we have an underlying rock or soil condition. For rock masses, we're generally concerned with rockfalls and debris flow. And for soil masses, we're generally concerned with landslides and mud flows. I showed this slide in the first live stream webinar last month, but I'll explain it again as a refresher. Possible rockfall solutions can be categorized into one of 2 methods. The first method is to control or contain the event at its origin. And the second method is to protect or intercept the event after its detachment. So conventional methods to contain or control surface instability at its origin include rock scaling and simple and pinned drapery systems. Soil nailing and rock bolting are used to control deeper instabilities. And then methods to protect or intercept the geohazard after its detachment would include a rockfall barrier or embankment, attenuator, debris flow, or shallow landslide barriers, which we'll cover during the next live stream next month. So methods to control and contain the rockfall event vary depending upon the nature of the instability. To mitigate against surficial instabilities, as shown on the bottom left side of the slide, a pin drapery system may be considered to contain the surficial instability of larger sized rockfall. If the instability is deeper within the rock mass, as shown on the right side of the slide, a more comprehensive global stability analysis would likely suggest rock bolting is necessary if the solution requires control and containment rather than allowing the rock to detach and intercept the hazard. Pin drapery and soil nailing systems consist of a high-strength steel wire mesh that's secured to the surface by a pattern of anchors. Rock or soil movement is controlled by the anchor mesh system. The mesh must control and contain the debris between 2 adjacent anchors. The steel wire mesh itself is a passive system, regardless of the anchor type. I will get into more detail about active and passive theory. And the anchors are usually passive nails, or they can be active tiebacks. The anchors are responsible for providing deep-seated global stability when needed, and are responsible to contain the volume of debris within the mesh. What I found in this industry is that there is no standard terminology, so I kind of apply my own. My terminology may or may not agree with someone else's, but here goes. When I think of a pin drapery system, I think of pinning rock, and when I think of nailing, I think of soil, as in soil nailing. In either case, we're talking about a system that consists of a steel wire mesh that's secured with anchors on a specified pattern. Explaining some of the differences, rock slopes are generally steeper because rock is stronger than soil. So it takes a steeper slope to create an unstable rock surface. Because rock is stronger than soil, the rock bolt pattern or spacing between the anchors to stabilize it is usually greater than a soil nail pattern. So rock anchors are often spaced greater than 8 foot apart, whereas soil nails are most often spaced less than 8 foot apart. Rock slopes are more often greater than 65 degrees, whereas soil slopes are more often less than 65 degrees, usually about 45 degrees. And as previously mentioned, in a pin drapery or soil nailing application, the anchors provide the global or deep-seated stability and are designed by a geotechnical engineer to provide a specific anchor diameter, length, and anchor frequency or pattern. The steel wire mesh provides only surface stability or strengthening between the anchors. Generally speaking, the further apart the anchors, the more strength or stabilization is required from the mesh itself. So in identifying the problem where we might consider a pin drapery, we're usually faced with a loose superficial zone of rock mass of a certain thickness. And in this loose zone, there are sets of joints dipping towards the slope, which create unstable conditions. So choosing the right mitigation system requires the designer to consider its placement proximity to the detachment area of the hazard and its most effective placement location. A pin drapery or soil nail system is placed close to the detachment area and extends from a higher elevation from the detachment zone. Here you see a perfect application of a pin drapery, where obviously you have a very legitimate and real geohazard potential with tight site constraint at the bottom of the slope. So there's simply no room for catchment of falling rock, and there would be a great negative impact to a highway or rail line if rockfall were to occur. So a pin drapery option is the best choice here to capture in place any loose rock that may become dislodged. Like any application, there are pros and cons to its use. Pin drapery can be expensive because of the drilling involved, but requires little long-term maintenance and is ideal where there are tight site constraints with limited catchment space for rock to accumulate at the bottom of the slope. Maccaferri drapery products are generically called composite cabled mesh. Composite cabled mesh, as the name implies, is a composite of double twisted steel wire mesh and high tensile strength steel cables, which are woven under tension into the mesh during the manufacturing process. These high strength cables run longitudinally through the mesh, and they can also be inserted laterally as well. Some of the benefits of composite cabled mesh include well, to begin with, the double twist wire mesh has traditionally been used as rockfall protection for over 60 years and is commonly used by state DOTs to restrain rocks up to 2 foot in diameter. So it has a very long track record of success and is a tried and tested system over a long period of time. One of the primary reasons is it's been so extensively used throughout the world is because the double twist wire mesh maintains its strength and does not unravel in the event of a single wire breaking. So as mentioned, the composite cabled mesh incorporates pre-tensioned, high-strength steel cables that provide very high strength with peak strengths mobilized at very low elongations. So this low elongation under load means less loading on the mesh anchor system and greater stabilization applied to the rock or soil surface. Here's a real life case. About a year and a half after this high-end residential complex was built in Edgewater, New Jersey, some rocks the size of a washer or dryer penetrated the roof of the adjacent parking deck and took out some cars. Other large rocks ricocheted off the bottom of the slope and penetrated an adjacent concrete wall to also hit some other parked cars. This prompted the owner to secure the adjacent 96-foot high vertical rock wall located only 4 feet away from the parking deck. A composite cabled mesh product was chosen for its high strength and ability to mobilize its strength within the deformation tolerance of the project site, while still allowing for an excessive anchor spacing. In this case, the interior anchors were spaced 50-foot vertical by 20-foot horizontal. As you see here, the mesh was loaded with a 2 to 3 cubic yards of rock and performed as designed while controlling the rock to about 4 inches away from the parking structure. This further emphasizes the need to consider the maximum acceptable deformation of the system on the proximity and sensitivity of nearby structures. As you see here, pin drapery applications often have an irregular and rugged surface from the underlying rock, and the plate loading on the mesh can be significant. Another important benefit of a composite cabled mesh is that the localized stress due to plate loading is absorbed by the high strength steel cables and deflect away from the base wire mesh. The Maccaferri SteelGrid HR30 is specifically designed to ensure that every plate captures at least one cable in order to deflect the plate load away from the base wire mesh. Maccaferri manufactures a composite cable mesh called SteelGrid HR. SteelGrid is manufactured with high-strength steel cables interwoven longitudinally under tension into the simple double twist wire mesh, providing ultimate tensile strengths up to 17,000 pounds per foot, mobilized at only 6% strain. So these longitudinal cables can be spaced anywhere from 20 centimeters apart, which is our SteelGrid HR20, to 400 centimeters apart, which is the SteelGrid HR400. Our most common product used is the SteelGrid HR30, where the cables are spaced 30 centimeters or 1 foot apart. And for more demanding pin drapery applications, the Maccaferri offers the RockMesh line of products, which have high-strength steel cables interwoven into the mesh in both the longitudinal and the lateral directions, providing the greatest punch and puncture resistance available in the industry. The RockMesh 3030, for instance, shown in the picture on the right, has longitudinal and lateral cables spaced on a 30 centimeter by 30 centimeter or 1 foot by 1 foot pattern, whereas the RockMesh 3100 has the longitudinal and lateral cables spaced on a 30 centimeter by 100 centimeter or 1 foot by 3 foot pattern. The solution offered by a pin drapery system consists of anchors, which play the leading role in providing stabilization to the rock mass, and the steel wire mesh then provides the surface stabilization between the anchors and keeps the rock from detaching between the anchors. So stabilization is offered through passive resistance, meaning that the mesh strength is mobilized only after deformation attributed to the loading of the mesh from the loose rocks. If the deformation of the wire mesh facing is high, the loose rock detaches from the surface and results in even larger loads that must be carried by the mesh and the anchors. Therefore, it becomes very important that the steel wire mesh facing be able to mobilize high strength with low deformation to provide stabilization to the loose rock. So performance of the mesh is determined by its stiffness, or the mobilization of its tensile and punch strength under load. This slide shows tensile strength versus strain characteristics of many different types of mesh. As you can see, the load strain response of a steel wire mesh is unique and can vary greatly from product to product. The ability of a mesh to provide stabilization is determined by the mesh's ability to mobilize its strength under load. So we've established that the stiffness of the steel wire mesh facing is characterized by its load strain characteristics. In the upper diagram, you see punch strength versus displacement curves of 3 different steel wire mesh products, and you'll notice the different degree by which the strength is mobilized. And in the bottom diagrams, you see an illustration of how each type of mesh may react to that load. With greater deformation, more debris accumulates within the mesh, which further increases the load on the mesh anchor system. So simply put, the quicker the mesh mobilizes its strength, the more stabilization it provides to the unstable rock mass, and the less loading that occurs on the mesh anchor system. So composite cable mesh mobilizes its full strength with very low deformations, only about 6%, and would be represented at the far left of these load strain curves in diagrams at the bottom. The anchor, of course, is a critical element of the design performance of the system, and as is the wire mesh facing, the anchor is also a passive element, which works only after the displacement of an unstable mass. So the anchor bar is completely grouted and cannot transfer forces between the plate and the foundation. In photos A and B, there is the development of a sliding surface of a large unstable rock mass. In photos C and D, to the right, there are details of the joint surface. We can see the rupture, and the movement is indicated by the two red arrows in photo D. Netting can only have a limited effect in controlling the movement between the joints because it is too flexible. But it does prevent many blocks of rock from coming away from the rock mass. And in this way, it helps the anchors perform their function, but only if the strength of the steel wire mesh can be mobilized. So as rock may reach its peak tensile strength at very low strain, it stands to reason that you would want your steel wire mesh to mobilize significant strength at those low strains as well. To complicate matters, the mesh can be difficult to apply because the ground is very rough, with many concavities and convexities. This also means that the mesh can never perfectly follow the slope profile, and a rock mass can always move and apply a load on the mesh. As we see in this force diagram, the mesh is not a beam, and there is no action by the mesh if it lies in a perfect plane between the anchors. In fact, the mesh starts its action only when the blocks of rock come away from the rock mass. So once again, to provide stabilization to the rock surface, it is important that the mesh has high stiffness, high strength at low deformation, in order to minimize the rock movement. So looking at how pin draperies are designed, we use a limit equilibrium analysis where we consider the ultimate limit state and the serviceability limit state, taking into consideration both mesh strength and deformation. In this analysis, we're considering the destabilizing forces developed by the sliding rock mass, and we're countering those forces with the resisting forces provided by the wire mesh tensile and punch strength. When the rock mass lies in limit equilibrium, we know the resisting forces are equal to the destabilizing forces. It is possible to implement a simple geomechanical model, as the free diagram shows, in order to calculate the destabilizing and resisting forces. In the ultimate limit state design, we consider that the mesh between the anchors is stressed, and the stress reaches its maximum at the anchors. The deformation of the mesh is calculated with a simplified geometrical model. So if the stress in the mesh reaches its maximum at the anchor locations, then it stands to reason that overstressing the mesh would result in greater stress acting on the anchors themselves. Since limit equilibrium analysis only considers safety prior to deformations occurring, you would want to limit potential deformations in order to maintain your safety factors. Otherwise, the more deformation that occurs, the higher the loading becomes, not only on your mesh, but also on the anchors. And this results in lower than expected factors of safety. So we've acknowledged the passive restraint offered by the pin mesh system. The mesh deforms when loaded. The amount of deformation in the mesh depends on the material properties of that particular mesh. And when the load in the mesh reaches its capacity, the restraint offered by the mesh is compromised. The loading on the mesh and its subsequent deformation is a function of the steepness of the slope, the strength of the debris, and the load strain characteristics of the mesh. Now turning to the serviceability limit state, we consider the acceptable maximum bulging depending on the sensitivity of nearby structures. In case 1, you see a structure at the bottom of the slope, but rather far away, and there is no structure at the top of the slope. So in this case, higher deformation may be tolerated. In case 2, you see a slope somewhat close to a roadway, so greater consideration of deformation is required. And then in case 3, with a structure at the top of the slope, that would be sensitive to slope movements, and an even tighter deformation requirement may be necessary. In designing a pin drapery, Maccaferri offers several design tools, including the MacRO1 design software, a theoretical design manual if you wish to review and verify the computer analyses. I've also developed some hand calculations that coincide with the theoretical design manual. We have product technical data sheets, product standard specifications, and typical drawings and details. We offer these tools complimentary, and we provide design consultation and preliminary design assistance as well. So feel free to reach out to us should you need any support in the future. For those of you that may be new to the Maccaferri offering, we have a suite of design software tools for your use. MacRO1 is for pin drapery, which is applicable to rock slopes. MacRO2 is for simple drapery design, also applicable to rock slopes. And then the MacS is a brand new design software for designing the flexible facing for soil nailed slopes. Today, we will briefly cover the MacRO1 design software, and as I discuss soil nailing in a few minutes, I'll also briefly introduce you to our MacS design program. The design method used is the infinite slope method, and is only for surface stability to verify the mesh and anchors, not for global stability. So there are 4 main categories of input for the MacRO1 design program. The slope geometry, the geotechnical and geological conditions, the mesh properties, and the anchor details. First, we'll input the rock slope angle and slope height. Then we'll characterize the thickness of the surficial instability. This is the thickness of the loose rock parallel to the slope. And we'll input the density of the rock. The program will also allow us to apply a partial factor of safety that takes into account the uncertainty of the geometric model. Next, we'll characterize the most dangerous joint. The problem is that we have a set of joints dipping in an unfavorable way with an inclination alpha exiting through the face. There is an assumed length of plasticization based on the fragmented or weathered condition of the rock face. We assign a joint compressive strength, a JCS, and a joint roughness coefficient, JRC, to characterize the strength of this most dangerous joint. Next, it is important to describe the behavior of the netting in terms of its tensile and punch strength and deformation characteristics under load. Maccaferri products have been tested and the results have been hardwired into the program, so the user only needs to choose a mesh type and proceed to the next step. The anchor pattern is input in terms of its horizontal and vertical spacing and its inclination into the rock mass. Other anchor parameters are also input, such as its diameter and yield stress. And the program also allows for an additional factor of safety to apply to the yield stress. Finally, the program allows the user to apply partial factors of safety towards the stabilizing forces, driving forces, mesh resistance and displacement, and anchor resistance and rock grout adhesion. Partial factors of safety are already hardwired into the program. However, the user may override them as necessary. When the design is checked and verified, the program calculates the factors of safety for the anchor bar and mesh ultimate and serviceability limit state. Since partial factors of safety have already been applied throughout the process, the final target factor of safety for each of these potential failure modes is 1.0. The program also provides the designer with the calculated results of the analyses. For the anchor bar design, you have the stabilizing and driving forces calculated, as well as the maximum pullout force and minimum anchor bar length required. And then for the mesh strength design, the program provides the actual stresses applied to the mesh, punching forces acting on the mesh, and the sum of the driving and stabilizing forces. The actual deformation of the mesh under the applied loads, as determined by product-specific testing, is then compared with the maximum allowable deformation in this serviceability consideration. And here's a few slides showing workers installing mesh, plating, when selecting a mesh, the most pertinent material properties to be considered when designing and specifying a pin drapery or soil nail facing system include the tensile strength and elongation, the punch strength and deformation, corrosion protection, and aesthetics. So here's a look at the tensile strength test in the top photo and the punch strength test in the bottom photo. Of course, the tensile strength test determines the load strain behavior in the direction parallel to the plane of the mesh, whereas the punch strength test determines the load strain behavior perpendicular to the plane of the mesh. Here you see three different products and their behavior to an applied punch load. In the photos to the right, from top to bottom, you'll notice the increase in deformation that can occur depending upon the product. The product on the bottom is made with a high strength steel wire, yet the manufactured mesh provides the highest deformation as compared to the first and second product. Therefore, it's not just the components of the mesh, but the method of manufacture for a given mesh that will determine its ability to mobilize its strength under load and ultimately provide stabilization to the slope surface. The performance properties of the system that should be incorporated into a design specification include the minimum required tensile and punch strength and maximum elongation or deformation of the steel wire mesh, its maximum opening size, the mesh maximum opening size, the minimum top cable, tensile strength and diameter, the maximum anchor spacing at the crest of the slope, the minimum anchor shear, tensile, and pullout capacity, the minimum interior anchor length and diameter, maximum vertical and horizontal anchor spacing for the interior anchors, and finally, any durability and aesthetic considerations such as coating type, weight, and color. These are the basic elements of any good pin drapery specification, all related to system performance. This chart shows the effect of coating type and weight on the corrosion resistance of the mesh. The Maccaferri products are coated with a zinc aluminum Galfan coating, which provides better corrosion resistance than 100% zinc. Our products are also coated with twice the coating weight as other products on the market, which further improves its coating corrosion resistance. For the most severe corrosive conditions, we can offer a polymer coated product called Polymac, which can further extend the service life significantly over conventional products, as well as provide an aesthetically pleasing appearance that blends with the natural environment. Aesthetics of the facing is often a major consideration for these projects, as the owner generally wants the product to blend in with the surrounding geology. There are four basic colors that Maccaferri supplies for polymer coated Polymac product: gray, black, tan, or brown. We can provide color swatches to help you assess whether a particular color that we carry would be acceptable for your project. If not, there is always the option to powder coat the mesh and accessories, and there is a much larger color range available which to choose. In the design of a pin drapery system, there is no one size fits all. So Maccaferri's approach is to design the system based on the project conditions and provide the appropriate mesh to meet the design requirements. As you see here, Maccaferri provides a range of products with varying tensile and punch resistance to accommodate most any condition. I like to provide our clients with some preliminary design guidance as a starting point as to what might be used in a certain condition. Of course, specific design analysis is always recommended. The primary takeaway here is that as the strength of the product increases, the anchor spacing may also increase. The SteelGrid product would generally allow for a 6 to 8 foot anchor spacing, whereas the RockMesh products would be considered for anchor spacings from 8 to 12 foot. And for the most severe conditions, our high energy absorption HEA panels are custom manufactured to provide the required resistance against extreme loading conditions. Here's some case histories now, some pin drapery projects. This is a project in Waltham, Massachusetts. It's a new Waltham High School, $375 million project. 415,000 square foot of school on 43 acres. And you'll notice in the back of the project, you'll see the rock wall. That's 1,400 foot long along, as you say, the back end of the site. Main drilling and blasting performed 875,000 cubic yards of rock blasting. GZA provided the anchor design. About 2,000 number 8 bar 10 foot long rock bolts were installed on an 8 foot by 8 foot pattern. Total rock wall area was 110,000 square feet, 120 foot high rock wall by 1,400 foot long. Haley and Aldrich specified the SteelGrid HR30 polymer coated black to blend with the natural rock. This is another project also in Waltham, Massachusetts. It's a commercial building, 300,000 square foot commercial building with a 900 car structured parking garage. The project required a 3-level 80-foot grade change. Once again, main drilling and blasting performed the excavation and pin drapery installation with GZA performing the anchor design. The pin drapery system included 700 number 8 bar anchors spaced on an 8 foot by 9 foot pattern and utilized about 60,000 square feet of the SteelGrid HR30. Here is a 210 foot high pin drapery necessary for the construction of this Walgreens in South Bergen, New Jersey. Approximately 54,000 square feet of RockMesh 3030 PVC coated black was installed by Philco Industries. About 110 number 8 bar anchors were installed on a 10-foot spacing along the perimeter, 6 to 8 foot into rock. And number 11 bar anchors were installed as needed throughout the interior of the rock face. Here is a case history of a reinforced cut slope along the Cascade Springs Scenic Highway, roughly 20 miles south of Park City, Utah. The Federal Highway Administration, Western Federal Lands, specified a pin drapery system utilizing high-strength steel wire mesh facing. The project consisted of 465-foot lateral length of slope, an area of roughly 35,000 square feet, to be pinned and secured for a 75-year design life. And of course, in this scenic area, an aesthetically pleasing solution was also required. The Maccaferri SteelGrid HR30 PVC coated brown was the system determined to best meet the project requirements. The slope height was an average of 60 foot and a maximum of 80 foot. Slope inclination ranges from 0.67 to 1 to 1 to 1. Anchors were spaced on a 7 foot by 7 foot pattern, 17 foot long. Here's a distant view of the project. The pin slope is the bottom portion of the upper slope, just above the highway, consisting of approximately 35,000 square foot of brown PVC coated pin mesh, underlain with a geosynthetic coconut matting. This next section is related to soil nailing, specifically the superficial stabilization due to the facing system. I'm sure you're all very familiar with soil nailing. We have an unstable soil slope that is reinforced in situ to provide superficial and/or global stability to a deeper seated failure. Then we're applying a steel wire mesh, referred to as a flexible facing system, that provides surface stabilization between the nails. So we're constructing the safe over-steepening of a new or existing soil slope. One type of anchoring system used is a soil tieback designed to provide an active pressure to the soil surface through the transfer of load from the plate and steel wire mesh. And another type of anchoring is the soil nail, which is usually not post-tensioned and is considered a passive anchoring system. The technique involves the insertion of reinforcing bars, usually installed into pre-drilled holes and then grouted into place, or hollow bars, which may be drilled and grouted simultaneously. In a soil nail system, the facing system can be classified as either rigid or flexible. So here I want to distinguish between protection and stabilization as it relates to the facing system. By definition, protection is to guard something against damage caused by outside forces. In this case, the system is internally stable. However, forces from the outside may cause erosion of the face. So on one end of the spectrum, an erosion control mat might be used at the face to provide surface protection, but it has very little strength and stiffness to offer any stabilization of the surface. That's why in a reinforced slope structure, the intermediate reinforcements are typically spaced 1 to 1.5 feet vertically when an erosion mat is used at the face. Stabilization, on the other hand, is the process of making something physically more secure or stable, requiring the facing system to provide greater resistance to the internal stresses that act upon it. Of course, in this case of a vertical retaining wall, the facing system required must have much greater strength and stiffness than the erosion protection mat shown on the previous slide, for obvious reasons. What's gaining great momentum these days is to apply a flexible facing system made of high-strength steel wire mesh secured against the soil face beneath the anchor plates. This technique is now being used throughout the world, oftentimes with a turf reinforcement mat either extruded onto the wire mesh or placed beneath it on the slope as a separate layer. In a flexible facing system with soil nails, similar to a pin drapery system, the steel wire mesh netting generally initiates reaction after movement occurs, identifying it as a passive system. The steel wire mesh facing is commonly referred to as a flexible facing system for its capacity to deform under load versus a rigid facing such as concrete. Historically, limit equilibrium methods have been used to dimension the steel wire mesh facing system. However, the LEM model does not consider any displacement or surface deformation, So the underlying assumption is that no deformation occurs. The problem with this analysis is that deformation of the mesh is necessary in order to mobilize its tensile strength and impart a stabilizing force to this slope surface. So explaining it in a slightly different way, a steel wire mesh facing is needed if deformation of the slope face is expected. However, the mesh tensile strength is mobilized only through deformation, thereby providing a stabilization effect to the surface. If the strength of the mesh can only be mobilized through significant deformation, then either you have a potential stability problem down the road, or the mesh is really only there offering protection rather than stabilization. Some research has been performed and documented by the Transportation Research Board of the National Academies. The research performed and documented in trying to determine whether a steel wire mesh imparts an active stabilizing force to the slope. The conditions for such an active force to occur includes, first, the mesh needs to be in intimate contact with the slope surface. And secondly, the mesh must be sufficiently stiff or stretched for the design loading condition to impart an active force. If these two conditions are not met, slope movement can occur and little to no slope stabilization is achieved. In that same research, the inspections of various secured drapery installations in California and Washington state found that despite concerted construction efforts, the steel wire mesh was commonly not in contact with the slope or could be easily lifted from the slope, and thereby providing a passive restraint rather than actively stabilizing the slope face as intended. Therefore, the design should be approached as serviceability first and ultimate strength second. The point is that a serviceability failure may occur when the design is based solely on the ultimate strength of the mesh. The design should be carried out with the understanding that prior to the ultimate capacity of the mesh being mobilized, its critical deformation may already be exceeded, as seen in the photo as the face bulging that has occurred. So understandably, the stiffness characteristics of the steel wire mesh facing system needs to be considered when determining a suitable anchor spacing for your design. Here's a look at some finite element analyses to show the deformations that occur at various locations along the depth of the slope. The dark blue line illustrates the deformations that occur without any wire facing at all. The green line illustrates the deformations that occur with a low stiffness wire mesh facing. You see that there's not much stabilization benefit, and the deformations are essentially the same as if there were no mesh at all. The pink line illustrates the deformations that occur with a high stiffness wire mesh facing. You see the significant reduction in facing deformation as a result of the quick mobilization of the mesh's strength at low deformation. This is the basis for Maccaferri's innovative hybrid design approach for anchored wire mesh towards a displacement-based design. And this is basically just illustrating the cost savings associated with using a higher stiffness wire mesh facing versus a lower stiffness wire mesh facing. Basically, if your anchor spacing is, say, 5 feet, 5 foot by 5 foot pattern, you've got an anchor every 25 square feet. If you're able to use a higher stiffness wire mesh and expand your anchor spacing to a 7 foot by 7 foot pattern, or one anchor every roughly 50 square feet, you've essentially cut the amount of anchors and the amount of drilling in half. And there's significant expense in drilling anchors. So by doing that, just by an incremental increase in cost of a higher stiffness wire mesh, you're significantly able to reduce the cost of your project by expanding your anchor spacing. Design approaches and dimensioning criteria for slope stabilization using wire mesh facing have been investigated since the beginning of the last century by means of empirical, theoretical, and numerical research. Diverse factors may influence the design process. Some are the slope geometry, the geotechnical properties and morphology of the slope, the type and position of the stabilizing elements, and many others. Standard design procedures are usually force-based approaches, often assuming oversimplified hypotheses regarding these different factors or the mechanical behavior of the system. On the other hand, accurate numerical approaches, for instance, ones based on advanced 3D modeling of the slope with a stabilizing system, they are available, but excessively demanding in resources, specifically time. So these conditions make evident the need for simplified methods capable of better analyzing the influencing factors, in this case, the soil mesh deformation. So as per a British standard, flexible structural facing soil nailing application can be used to provide long-term stability of the face by supporting the soil between nail locations and transmitting the load from the soil to the soil nails via the nail heads. Flexible facing may be used to provide support through the mobilization of tensile forces within them, and therefore some deformation is required for a component of these forces to act normal to the face. In the design of flexible facing with soil nails, a two-part wedge method of analysis is considered, where the maximum unstable volume of soil is calculated, and the result is a sliding surface close to the slope face. On a post-intervention stability analysis, a pressure Q is imposed by the mesh. Is then introduced to increase the initial safety factor. So for slope surfaces, it's common to look at slope parallel instabilities, which would consider the shearing of the anchor associated with a column of thickness of soil sliding along a plane parallel to the slope face. And then between the nail instabilities associated with the soil forces that mobilize between the nails and exit through the face. The steepness and internal strength of the soil slope, the density of the nail pattern, and stiffness of the facing are all considered in the stability analysis. Common design procedures use an approach based on the limit equilibrium model, which is stated as the driving E, which is the driving action, is equal to R, which is the mobilized soil strength or the resisting forces reduced by a factor of safety, plus A, which is the stabilizing action provided by the anchor and mesh system. The LEM assumes that the protective mesh behaves like a rigid structure, able to develop the required resisting force and transfer moment without considering the deformation of the system. However, this is counterintuitive to the concept of flexible facing. As mentioned before, the analysis of a flexible facing system should consider the deformation to account for the maximum forces that could be imposed on the wire mesh and anchor system. So first presented by Galley in 2017, the hybrid approach considers the deformation field of the soil to calculate the value of the maximum stabilizing action from the mesh and the anchors. This hybrid method approach is a combination of the ultimate limit state and the serviceability limit state. As in the LEM approach, the soil is considered at its ultimate limit state. Thus, the Moore-Coulomb criterion for the shear stress calculation applies. On the other hand, the mesh and nails selected for slope stabilization is considered at its serviceability or elastic limit state related to the interaction and deformation of the stabilizing elements. So hybrid methods rely on this soil structure interaction model, which is defined by a characteristic curve. And this curve expresses the value of the stabilizing action as a function of the displacement of the soil. Indeed, only a proper description of this interaction allows an accurate quantitative evaluation of the stabilizing action, and thus the definition of safe design solutions. To reiterate, the characteristic curve describes the interaction and deformation behavior between the specific mesh, anchor, and soil system. It's a function of the soil properties, the mechanical characteristics of the mesh, and the anchor spacing. So as the soil element deforms in step 1, it induces a pressure Q against the mesh, which generates a tensile force T on the mesh and a tensile force F on the anchor. 3 key concepts deriving from the introduction of the characteristic curve are first, the influence of the soil mesh relative stiffness on the stabilizing force, affecting also its peak strength value, can be explicitly captured. The safety level of the superficial soil layer of the slope in presence of the stabilizing system becomes a function of the soil displacement pattern. And the working condition of the mesh for the desired safety level of the superficial unstable layer can be evaluated. So here I'd like to introduce you now to a free online soil nailing design tool called MacS Design that uses the hybrid approach to design wire mesh facing for soil nail applications. I'm not going to go into detail into all the detail of the program now, but we can provide you and your team a webinar specifically devoted to this design program anytime in the future as you'd like. A brief example of how this characteristic curve is used to design surface stabilization of soil slopes using steel wire mesh. We will go over a simplified schematic of algorithm used on the proprietary software named MacS Design, developed by Officine Maccaferri in collaboration with the Civil Engineering Department of the Polytechnic of Milan. So MacS Design is a design tool which can support engineers to design soil nailing systems with steel wire mesh for slopes, superficial slope instabilities. So here's a quick tour through the interface of the program. It's a very powerful tool and a revolutionary hybrid design approach that takes into account the potential deformation mechanisms in the evaluation of the safety of the solution, the stiffness and punch resistance of the facing, nail and soil stiffness, and groundwater and drainage conditions. There are a series of drop-down sections where the designer inputs various design parameters. You see in this slide the drop-down feature for the slope geometry, input parameters. Then each individual green section drops down to input geotechnical parameters, water table information, partial factors of safety, and seismic coefficients. Here's a view of each section fully opened for input. An analysis is conducted to determine the slope factor of safety without any stabilization provided. And then the stabilization system, including the mesh and anchor information, is input for final design analysis. So I just wanted to pique your interest here a bit with these few slides. And like I said, if you're interested, we can go into that in more detail at a later time. So the Maccaferri products specifically designed for use in soil nailing applications include the MacMat R and the MacMat HS. Our lightest weight product and therefore lowest strength is the MacMat R, which is very commonly used in soil nailing applications where vegetative growth is desired and achievable. For those of you that are familiar with our simple double twist wire mesh, the MacMat R consists of a turf reinforcement mat extruded onto the double twist wire mesh to provide surface stabilization and erosion protection to facilitate vegetative growth. This product is most commonly used on one-to-one soil slopes with a 5 to 6 foot anchor pattern. The MacMat HS combines the SteelGrid and MacMat R technology by extruding the turf reinforcement mat onto the SteelGrid HR product to provide a single layer product that combines very high surface stabilization with erosion protection. This product is most commonly used on steeper slopes and or trying to optimize the nail spacing to a 7 or 8 foot pattern. Finally, we'll go through some case histories of some soil nailing projects. In this case, there was a failure following the failure of a cut slope, 40 foot to 100 foot high, 650 lin foot along a rail track. The decision was taken to stabilize this cut slope using 680 soil nails, 20 foot long, placed in a staggered pattern with a high strength steel wire mesh facing. In addition to being high strength, the mesh's low elongation was also considered important as the acceptable maximum deformation of the facing system was limited so as not to interfere with the rail right-of-way. The general contractor approached Maccaferri for the supply of a suitable high-strength steel wire mesh product for the stabilization of this cut slope. Maccaferri worked closely with a designer to establish the most suitable product for the stabilization and found that the SteelGrid HR30 was deemed to be the most appropriate material with its tensile strength of over 12,000 pounds per foot at only 6% elongation, and its in isolation punch strength in excess of 11,000 pounds with less than 10 inches of displacement. The wire mesh was installed over a biodegradable erosion control mat to help facilitate vegetation. The owner of this project was the Virginia Division of Mines and Land Reclamation. The left photo is a view of completed soil nailing work behind a private residence in Grundy, Virginia. The slope was being continually subjected to erosion where unconsolidated soil and rocks would slide down the slope and end up endangering the structure. Multiple scarps were present on the hillside, indicating the presence of active shallow landslides, a more serious slope instability than solely superficial erosion. The shallow landslides resulted in larger portions of the hillside dislodging and traveling downslope, leaving an oversteepened scarp behind them. Then new shallow landslides initiate upslope from previous ones as the new slope geometry is often unstable. The slope at the project site ranged from 28 up to 83 degrees. Where the scarps were present. Generally, the slope was at an angle near 38 degrees and about 100 foot long by 60 foot wide. The solution consisted of soil nailing with the placement of RockMesh 3100 and MacMat for surface stabilization and revegetation. This project was along a major expressway linking residential and commercial developments on North Santiago Boulevard in Anaheim, California. The problem that needed to be addressed here was that the highly erodible steep slope along the roadside was prone to frequent mudslides. The solution consisted of soil nailing the slope with 9 foot long anchors spaced on a 6 foot pattern with the Maccaferri MacMat R steel wire mesh facing. And here, as you see, this was a massive landslide, shut down Highway 101 south of Crescent, California in February 2021. This is a UNESCO World Heritage Site of Native American tribe lands in the Redwood National and State Park. These redwoods exceed 300 feet in height and are over 1,000 years old. Carlson's Construction was contracted to provide slope mitigation and contacted Maccaferri for various options. Maccaferri supplied 175,000 square feet of pinned RockMesh 3030 powder coated black for aesthetic purposes. Over 2,200 anchors and spike plates were used on the project. So far, this system has survived and prevented further erosion during the historic 2022-2023 winter rains. I'd like to thank you all for attending today's webinar. It's like we went a little bit past the hour. I hope you gained some valuable information. Like I said, if you're interested in having more information on various products and applications, we can provide you with a Maccaferri Rockfall thumb drive that includes all our information. We also include technical publications, technical data sheets, typical drawings, and product standard specifications for your use. Feel free to reach out to me directly by email. You can also find my information on our website. Also, if you're interested, as I mentioned, in any of our design software programs, such as the MacRO1 and 2 for Rockfall Drapery applications or the MacS Design for soil nailing, we're certainly willing and able to provide webinar tutorials to your firm. Please look out for future advertisements for our third Geohazards Mitigations live stream on April 23rd. The topic will be on dynamic rockfall barriers, hybrid barriers, and attenuators. We offer 1-hour PDH certificates for any of these webinars, so please feel free to email me if you're in need of one of those. Anyway, I'm free to have any questions. If you all have the time, I have the time. If there's any questions, we have plenty of time.
Well, thank you, Mike. It was a very good presentation about slope stabilization and great examples. We have a few questions from our watchers in YouTube. First one is David Field. He's asking, how can you clean out accumulated loose rocks restrained by the system?
Yeah, good question. You basically detach the plate and mesh and let the rock fall to the bottom in a controlled manner, and then clean it out just by the same way, detaching periodically, just detaching and controlling the movement of the rock.
All right, thank you.
And then you can reattach the mesh and the plates.
Great. Bob A is asking, if this system is designed and used, who is considered the designer of record? Maccaferri?
We do not stamp and seal, provide final design work. We work with local consultants. If you're a local consultant, we would work with you, provide you with preliminary design, provide you with analyses, make sure you're comfortable with everything. If you're not interested in doing that, we have engineers, independent engineers throughout the country that specialize in this technology that would provide final engineering.
All right, thank you. Next one is Lawrence Susanathan. Are any pull-out tests performed on site after installation of the pins/anchors? Will the mesh need to be replaced after experiencing deformation from rockfall, etc.?
So yeah, usually there is a certain percentage of nails that are tested to ensure the load capacity is achieved. But to answer your question about the mesh does not need to be replaced. If usually there's no breach in the mesh. Usually that's the case. So certainly the mesh wouldn't need to be replaced so long as there's no breach in the mesh. If there is a breach in the mesh, then it's easily patched.
Okay.
Yeah.
Cool. Dr. Bazam Toma, what is the projected service life of the mesh? And what happens when this period is over and protection is still required?
Okay. Yeah, good question. Usually the mesh lasts much longer than we expect. The service life is much greater than what we might suggest, and that is because we're generally conservative in our estimates. Of course, service life is a function of the corrosive environment that we're dealing in. So let's say a standard galvanized product in a place like Hawaii or Puerto Rico, where it's subjected to the salt spray from the ocean, that's not going to last very long. Just unprotected galvanized steel is going to rust pretty quickly. Could be a year or a handful of years. Galfan will last a little longer, but in those environments, we would polymac coat the product. Or if the budget allows, in Hawaii, for instance, we've sold a lot of stainless steel product. So that's always an option. Stainless steel that would be powder coated. So there's polymac coated or stainless steel that would be powder coated for some color. Those are going to last, those items are going to last, we would say 75 years plus in a highly corrosive environment. Under normal conditions throughout the mainland US, the galvanized product or the Galfan product will last in excess 30 years. And like I said, that's going to be conservative. I think that's all I can say as far as giving any details without really knowing the corrosive environment that we're dealing with. But that's one of the factors that's looked at in design phase, is what is the potential corrosive environment of the installation, and is there anything that we need to do differently with the product, or is a standard Galfan coated product going to survive 30, 40, 50 years. That's usually the target time frame, is that 30-year time frame, is usually 30 to 50 years is the target time frame.
Great, thank you. Next question is from Francisco Silva. How do you service a mesh that has developed butt bulges due to rock or soil accumulation? Do you need to remove the entire mesh?
So the rock part of it is easy. The rock will generally accumulate, and then you'll have to detach the mesh and periodically inspect to see how much accumulated mesh is occurring. Maybe that maintenance occurs once a year to inspect and see whether there's any significant accumulation in any particular area. But if there is, then there's just a method of detaching the mesh and cleaning it out and then reattaching the mesh. That's for soil slopes, if it's designed properly, you shouldn't get much movement of unless the spacing of the anchors is just excessive. In that case, the superficial problem still exists. So proper design, and the design that we would adhere to, which is our hybrid design, where we take into consideration the serviceability limit state and the ability of the mesh to provide stabilization, should prevent any surficial problems. So proper design, you shouldn't see sloughing of the slope face.
All right, thank you. Another question from our viewers is Arun Kumar. Is soiling means just injecting a steel rod / tender, or it's like injecting cement slurry inside a steel tube kind?
Okay, so yeah, the two types of anchors that are typically used in soil nailing are going to be a grouted rod, or a hollow bar, where it's grouted at the same time. So in both cases, they're passive elements, and it's grouted in place.
All right, thank you. Question: the blending of the mesh is always required, or it's something required by the client?
Well, I'm sorry, say that again.
The blending of the mesh when in a slope, it's usually required, or it's just a client decision?
There's a difference between the West Coast and the East Coast on this, but usually aesthetics is an issue, is a concern. The products are in mountainous areas, scenic areas, and there's generally the client wants a natural looking environment to be maintained. So normally coloring, most of the time, the vast majority of the time, color is a big part of the design and required. If it's a temporary application, then color doesn't matter, obviously. And then, of course, there are areas of the country where a galvanized or galfan product, a gray color, actually does blend in well anyway with the rock, and that's why one of our polymac colors is gray. So most of the time, color aesthetics is a big part of the specification. Yeah.
All right, thank you. Last question: what is the maximum plate load for the Maccaferri products?
Yeah, that's a good question. So for soil nails, which are a passive element, the anchors are not pre-tensioned. So the tightening of the plates should be so that it creates the full contact of the plate mesh soil. So 10 kips is really all you should really need, although the mesh soil system can handle a lot more than that. For instance, for our composite cabled mesh, our standard spike plates are designed to capture at least one, if not two, of the high strength cables. And then these cables are 5/16 inch diameter. They're 8 millimeter in diameter. So, so if the plate catches both cables, the system can absorb up to 90 kips of plate load. If only one cable is captured, then it can handle about 45 kips. But if no cable is captured, the wire mesh soil system can still withstand much more than 10 kips.
All right, thank you. And maybe this is the last one. How steep of a soil slope can be built with the Maccaferri products? Because in one of your examples in Massachusetts, you have very steep rock wall, but looks like you guys did the installation only on the top.
So, the FHWA differentiates between a slope and a wall at about 70 degrees. So that's typically, the cutoff. We talk about walls in excess of 70 degrees and slopes less than 70 degrees. So for For soil nailing applications, up to 65, 70 degrees would be practical for permanent conditions. We have done cases where temporary shoring, for instance, under a bridge, 10 or 20 foot high, up to 20 foot high or so, we could go vertical, like I said, under temporary applications. Once again, it's a function of the type of soil. So if you've got some soil that's got some cohesion to it, and like I said, it's a temporary application, then we could go vertical. But for permanent applications, for soil nailed slopes, less than 65, 70 degrees.
Thank you. Well, thank you everybody for the questions on the YouTube chat. And thank you, Mike, for this great presentation. Now, Brad, the microphone is yours.
And I'll take us home. Great job, Mike. That was a good part 2, and Christina for handling the questions and adding on a few of your own there at the end. As Mike mentioned, we have 1 episode left in the Maccaferri series, and that will be April 23rd. We hope to see everybody back here for that. If you enjoyed what you saw today, and if you're here at the end, you probably did, of course, click like, subscribe, and get notifications. We'll let you know every time we post something to the YouTube channel. Our next YouTube event is not even a live stream, but it's Thursday morning. It's our latest Geo Legends episode featuring John Burland of Imperial College London. That is going to be a good one. Well, I know it is because I'm editing it. But you want to tune in for that at 10:30 on Thursday morning. And our next live stream will be April 2nd at 2 p.m. Eastern Time as usual. And that is the Geo-Institute 2024 annual business meeting. So we'd love to see you back for that to hear about the state of the Institute and ask your questions to the GI board. So Mike, thanks again for doing this. Fantastic job. We'll see you back here in a couple of weeks for episode 3. Christina, excellent job in your first moderating gig. And our producer today was Matt Roberts, and we will see everybody very soon.
Thanks. Thank you, Brad. Thank you, Christina. Thank you, Matt.
Bye.
Thank you all. Take care.